Welcome to springlib.
Okay, so we want the minimum thickness. If we know that glass is going to appear dark if 680 nanometer light is incident on it. Air between two glass surfaces. Let's go ahead and draw this out. Glass, glass, air. So we're going to have light coming in through here. Of course, some will reflect off here. I think based on the fact they don't really give you any information about the glass, we can't really kind of assume that we're comparing this photon and like this photon. It's all about what's going on with this air and the thickness of this. And so we're concerned with the relationship between these two photons. We know that their wavelength is 680 nanometers. Is that what it said? Oops. Yeah, okay, and then we want it to appear dark. Then that means that the phase difference between these two photons, delta phi, so that's going to be, let's say that's the second photon, and let's say this is the first photon, that's going to be phi 2 minus phi 1. Phi 2 is going to, so what kind of phase is this going to accrue compared to phi 1? Well, it's going to get a phase as it goes through here, and then this air section. So that phase is going to be 4 pi n times the thickness divided by lambda, and that just comes from the fact that generally in a sine wave that the phase evolves as 2 pi, a sine wave of, of wavelength lambda, that it's 2 pi, oops, sorry, not over k, over lambda times the distance that it goes, and the distance in this case is 2t, and then lambda goes to lambda over n. Oh, and now talking this out, I actually discovered this mistake. Well, this index of refraction in here, it's just 1 because it's air. So that's what this looks like. And we want to set, for destructive interference, we want to set this equal to 2m plus 1 times pi, just to say we want an odd integer of pi as a phase difference. And so now we can solve for the thickness, and we can say that it's lambda, the pi's will end up canceling. So lambda times 2m plus 1. Oh, I forgot to do the phase difference is due to reflection, my bad. So let me go back to this part of the equation and kind of stick it in here. So phi 1, it's going to undergo no phase shift because it reflects off of a high to low surface, but this is going to undergo phase shift. So phi 2 will undergo 1. So this is going to be plus pi. And then I can subtract a pi over here. So then that's just going to be just plain old 2m. And yeah, so then now I can kind of continue. So it's going to be lambda times 2m over 4. So it's going to be lambda over 2. And then m is just going to be an integer. So we want the smallest integer. So it's going to be m is 1. So we can just evaluate lambda over 2. Ooh, and I can do that in my head. So that's 340 nanometers. And that would be for dark. If we wanted to appear bright, let's think about how we modify this process. And so that would mean that this thing would just be 2m. So like this is going to be my dark. And then I guess I'll do my bright work in green. So this becomes 2m. And then now we have this plus pi over here, so we have to bring it over. So then the thickness is going to be lambda over 4 times 2m minus 1. So we just want an odd. So this is basically what's the smallest odd number we could do. That's just 1. So it's going to be lambda over 4. So we'll divide this again. Oh, and I can also do this one in my head. So this would be 170 nanometers. And this would be dark. So that's kind of this answer. I'm writing it huge for some unknown reason. And then this is going to be bright.